All right, welcome. So in this video, I want to continue talking about analyzing loops, but now I want to introduce how we can use summations to analyze the number of operations used by a loop, especially in cases where the loop is maybe a little bit more complicated. So we concluded our last video by taking a look at this loop in the minimum algorithm that we've been looking at. And we actually did a sort of high-level analysis, one that didn't take into account many details or many operations. And we only actually focused on how many assignment operations are carried out by this algorithm. Sometimes that's a very useful technique to do analysis. One reason it's useful is it can be very simple to only count one kind of operation instead of counting all of the relevant operations. And then sometimes maybe that one operation is actually a very important operation. A good example of that might be when the operation is communicating over the network on the internet. Why would we privilege that operation and only want to count that particular operation? Well, those are usually time-consuming operations. They take a lot of time. So if we have to make a request from a website 100 times, that's probably worse than having to make the request only a handful of times. And so if those type of operations are showing up in our algorithm, those really time-consuming ones, we might focus only on those operations and see how we can minimize them, even if it comes with a trade-off for spending more time on other operations, assuming those other operations are shorter or smaller or take a less amount of time. However, from our context and the perspective that we've been looking, we're not at such a high level. We're more in the middle range. If we're sort of a Java or JavaScript programmer, we probably exist in that middle range where most of the operations matter to us, but most of them are constant time operations, meaning we can roughly count them for taking one operation or maybe two or three, and we'll sort of wave our hands at that. Now, for our purposes here, like I mentioned, we were only counting assignment operations, and the key to our counting came with this for loop. We wanted to count how many times this particular operation was carried out. And we did a little bit of internal logic. We said, hey, this loop started at 2 and it goes to n. That gives it n minus 1 opportunities to carry this out. If we assume we're in the worst case, where every time we hit this branch, this if statement, we do indeed carry it out, then n minus 1 is sort of the exact number we would carry out. Or we can think of it as an upper bound, the most number of assignment operations that we might actually carry out by this loop. Now, one way we could express this here is we could say that every time we go through this loop, in the worst case, we do one assignment. So that's represented here by the 1, and we could say every time we hit this loop, we do another one. So it's 1 plus 1 plus 1 plus 1. And that logic we put in there in our argument to come up with this number n minus 1 was saying that, hey, if we did this starting at 2 and went up to n, and if you don't believe me, you can sort of write an index here, 2, 3, and so on. Write them up, all of the ones that you want, all the way up until you get to n, and then count them up, and indeed you will find there are exactly n minus 1 ones there. And of course, hopefully we are skilled enough with our arithmetic that we know that if we take 1 and we add it to itself n minus 1 times, we get n minus 1. This is sort of the basics of summations and addition that we're already familiar with from studying arithmetic. However, in mathematics, of course, we have a notation that we use to symbolize this type of summation. Here I've used the ellipsis, the dot, 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 and I've used this sort of bracket on the top to capture them. This notation is a little bit cumbersome, and so we don't usually use this type of notation. Instead, we're going to use what we've called the summation notation, which most of you have probably seen before, using the capital Greek letter sigma, which I presume is the first letter of the word sum in Greek, though I don't speak Greek, so I don't know. I'm just assuming that. But that is the symbol we use for a sum, this sigma here. Again, some of us may have seen that, but let's go through this to sort of see exactly what this means. Is where summations actually are great tools for analyzing loops, especially for loops, because as you can see here, I'm using the exact same index that I was using in my for loop. So fairly straightforwardly, I'm able to just copy down what I've got written up here into my index on my summation. This is saying do the summation starting at I equals 2 up to I equals n. So that's the same thing that this for loop's saying here. And then what is this value here is the term we're going to be summing over. And in this case, it's just saying it's 1. Okay, and so again, this expression here that we've got here is supposed to capture the number of assignment operations carried out by the for loop. And well, what I've got going on here with a couple equations, if we jump to the end here, we'll say that this notation is meant to just express what we've got up here as well. Okay, well, that's what our sort of internal logic already captured. The other thing I want to note here, and this is sort of the interesting step here, this first summation I created by just copying what I had in my for loop up above, and now that's going to work a lot of the time. Some of the time it won't work, but a lot of the time it will. But when we get down here, once we've moved from the actual code where the fact that we started at 2 and went to n mattered, when we translate that into now a mathematical object, the summation, starting at 2 and n no longer really matters. We're not checking here. Here we're just adding things up. So we can actually do a change of indices. Here I've decided to subtract 1 from both the starting index and the terminating index. So that gives me 1 and n minus 1. Now this is something that we sometimes can do and it will not change anything. The reason we know it will not change anything in this case is because the term we're summing over here, 1, doesn't have the value I showing up in it at all. Think for a second what would happen if we did this where we had an I written here instead. In fact, let's consider what happened. So I have the sum of 2 to n, but let's say we had I in here. Now notice this is going to be completely different than what we had written over here. Maybe I'll just write out what this is since we're taking a look. This would be 2 for the first value because I here would be 2. But the second one would be 3, and then 4, and then all the way up to n. Now notice this is a completely different sum than the one we've been looking at. The one with all ones is considerably easier to figure out than this one. This one I'm going to delay for a little bit to solve, but we'll come back and solve that later. The point that I was trying to make here is imagine in this example I've just decided to do, I think I said minus 1 to each of these terms. Let's see if we do that. For this sum, I equals 1 to n minus 1. I just did minus 1 on my starting index and minus 1 on the terminating index. If I leave it here as just I, now if I write out what the sum would be, it would be 1 plus 2 plus 3 plus all the way up to n minus 1. And that's not what we want actually. If we do that change, that doesn't keep it the same. These are no longer equal. If we wanted to make them equal, by making minus 1 on the indices, I'd have to do plus 1 on the value that we're summing over, the index I here. So anytime I would show up in my formula here, I would have to, if I did minus 1 out here, I'd have to do plus 1 over here. And now you'll notice that would change that to a 2, that to a 3, that to a 4, and finally that to an n, which now these would be equal to each other. So we could do that, but now what was the sum we were looking at? We were looking at I equals 2 to n of 1. And I'm saying, in this case, when I do minus 1 to each, I have to do plus 1 to each occurrence of I in this formula. Well, there's no occurrences of I in this formula, so I'll just leave it as 1, which gives us the n minus 1 that we were sort of arguing there. So that's what I've done in this little step here, is I've really just subtracted 1 from the starting and concluding index for my summation. That gives me from this step to this step. But because I does not show up in the term we're summing over, we don't have to change it at all. And so we actually get the same value for these two sums, which is just n minus 1, as we argued already. Now, I've sort of used a notation In the previous slide, a more general, or not the previous slide on the whiteboard there, where I noted that this term that we're summing over could change. It could be dependent on I. And so in general, I've just written that here as a sub I, where we would be adding a1 plus a2 plus a3 and so on, up to, again, some maybe terminating condition here, an. Now again, we've been using this terminology. This is what we call a summation. If you've encountered this in other math classes or in other studies, you might also have it been named a series. In this case, we're dealing with what we might call a finite summation or a finite series, where the number of terms is a finite number. So we have an upper bound of n here. Although we can also consider infinite series or infinite sums. You may have encountered that, say, in a calculus class, and in which case the upper bound might be infinity. And we may see one or two of those sums down the road, but we're going to focus primarily on finite sums. And part of the reason for that is, again, because we're wearing our computer science hats, which is we are mostly dealing, the purpose of wanting to use subs, at least right now, is to express the running time of a loop. Loops are typically finite, so we usually just work with finite sums. Or maybe another way of saying that is, if our loop is infinite, well, it takes infinite time. We don't have a lot of analysis to do. If we have an infinite loop, we know it's going to take infinite time. So we're most of the time, again, 90, 95, 99% of the time, we'll have finite series, but every once in a while there will be a reason why an infinite series might be important to us too. So we'll take a look at that when they become important. So I wanted to start with a couple of just simple, I've got them set up here as theorems, but they're really just rules, if you like, rules of thumb that you could put on a little summation practice sheet. The first one here is what I call the simplest sum of all. If you're just adding 1 to itself n times, you just get n. And again, this is so simple, you might just put it on your cheat sheet to remind you, or it's so obvious you already know it. But I've included a quick little proof here. It's hardly more of a proof than just applying the definition of the sum and seeing what it is equal to. So here I've just expanded the summation into the more cumbersome notation with the ellipsis, and just noted that 1 plus 1 n times is n, which we should know. Okay. Again, to make it a little bit proofy, I just start out here with this assumption that n is a natural number. This is actually critical and important, something I maybe didn't say when defining what a summation is, but it is something that we are maybe assume that the type of number that we sum over here has to be a natural number, a counting number. Technically, we could use integers as well, but not rational numbers or real numbers, and so that's important. And that's also going to be true largely if we're doing a simple for loop as well. We usually use an integer data type where we increment. Of course, once we use a for loop in programming, we have a little bit more power, but summations always have a natural number most of the time. Occasionally we might have an integer if we want to start in the negatives. We might have an integer, but still whole numbers. They must be a whole number, no fractional components allowed, no rationals or irrationals. And so the other thing that we must mention is that summations also always count up, and they always count up by 1. So we can make for loops quite easily that count down or count up by 2 or 5 or 25, whatever we want. When we translate those loops into sums, we have to respect that the mathematical rules do not allow us to do that. We have to increment our index by 1 each time, and so that's what's assumed here. Now, if our for loop already does that, and again, a whole bunch of our for loops, that's just how we design them, then perfect, we just translate them directly into sums. Otherwise, we might have to be a little more careful. Okay, what about our next little rule here? The only thing I've changed here is, what if I change from 1 to n if I just go a to b, any a to b? And here's where we might say, well, these could be integers now. Maybe it's I equals -5 to b equals 5. How many values in that range? And at the moment, at the top of your head, from -5 to 5, I don't know what your answer, you might have an answer in your mind. But there's two that I think that you might come up with. Some of us might say there's 10, because 5 plus 5 is 10, and that makes kind of sense. But that's forgetting the 0. There's really 11 because there's a 0 in there, right? There's 5 positives, there's 5 minuses, and then there's the 0. And that actually helps us capture why there's an important, that we have this plus 1 in the formula here. It's not just b minus a. Our instinct might be b minus a, take the upper bound and minus the lower bound. That actually does not include the lower bound itself. It ignores the lower bound. So again, I've just got a little bit of a mathy bit here, but what I'm doing here is I'm using that same trick we used in the last example where we started at 2 to n, where I'm saying just subtract off. Now here actually I'm going to do it in 2 steps to sort of see what I'm going to do. First I'm going to subtract off a. That's going to make the first one actually 0, right? Not 1. But I want it to be 1 so I can apply this formula up here. So to do that I'm going to plus 1 to both of them again. So I plus 1 to both of them again. Okay, that puts it now in this format where I can apply this formula, which tells me all I need to do is read off the upper bound. That happens to be b minus a plus 1. Again, I usually just put this on a little practice sheet or cheat sheet for me, that whenever I have to, look this up, if I can't remember it off the top of my head, that it's b minus a plus 1. It's usually the plus 1 is the only thing you need to remember. The b minus a is very intuitive, but we sometimes forget that plus 1. So I might keep that on a little cheat sheet somewhere as well. I don't really need to prove it to myself every time. And then the last little one, this really I'm just going to leave as a rule. I'm not going to place it as a proof in any format, is what happens to follow the distributive law. And maybe I won't formally prove this, but I will just, let's say, informally prove it by reminding us of what the distributive laws are. So here I'm using a d. So let's say we had something like this, d times a1 plus a2. Okay, now this, I've written it this way, but we can probably know by our distributive law from arithmetic that this is going to be dA1 plus dA2. And, well, the law works both ways. When we go this way, we say we distribute it. When we go this way, we usually say we factor it. And it usually depends on what we're doing in our math, which way we want to go. Sometimes we want to go one way, sometimes the other. Well, we can rewrite this, and maybe I'll rewrite this very deliberately. On the left-hand side, I can write this as d times the sum of I equals 1 to 2. I only had 2 in there, of AI. And then what I could say here, writing it this way, is I could write it again, that this is equal to I equals 1 to 2 of d times AI. Basically what this rule is saying, now the rule I have out there just changes this to an n and this one to an n as well. What this rule is saying is just that we can factor out the d, or we can distribute in the d, depending on which direction we want to go here, left to right or right to left, as long as something is true of d. And it's pretty clear here what it is, which is it doesn't depend on I. Okay, AI is very clearly, because of the I in there, the subscript I, it does depend on I, and so we can't factor it out. By factoring it out, we kind of lose definition of what I means. I is defined by this sum here, and once we move it out, we no longer know what I means. Okay, we can only really move that out by doing what we did from the top line to the bottom, which is changing notation from one notation to the other and just listing out all the different elements. Now, all we're trying to get here is that this particular arithmetic rule carries over into summations as well, which is pretty intuitive and obvious for those of us that are pretty comfortable with our arithmetic, that we can apply this distributive law in this notation as well. Now, this tool here, the factoring out, is probably one of the most important tools we use when we're simplifying summations. Usually what we want to do is focus in and find what component of the term we're summing over that doesn't depend on I, and just move it out front. As soon as it's out front, it makes it typically easier to focus in on this sum and figure out what it is equal to. And we'll see that maybe in a couple of our examples. Okay, so now what I want to do is use this technique of using a summation to do analysis on a for loop to do a more fine-grained analysis than we were doing earlier, okay, which means taking into account more operations, more details than we did before. Before we only counted assignment operations, and maybe let's just revisit that conclusion. We've said a couple times now that there's n minus 1 assignments here in the worst case, but counting these two other assignments, we got to our conclusion of n plus 1 assignments. But now we might want to ask ourselves, well, how many other operations, or maybe not other operations, but how many operations in total, including the assignments and the non-assignment operations? And we had already gone through and sort of highlighted on each line how many operations we thought would be carried out on that line. And as a result, we can now use these observations with the tool of the summation to complete the task of counting all of the operations. So let's see if we can do that. Now, usually what we're going to do is we're going to, or at least the way I do is I'm going to split my analysis up into different chunks that are easier to analyze. And these chunks are going to correspond to the logical chunks of the program. So we're already splitting up the algorithm and the program into these logical chunks. Well, typically it makes sense to analyze each of those chunks itself. So the chunks that I'm concerned with here are before the for loop, so this business, and maybe the setup for the loop, we'll see, the actual loop, and then after the loop. And some of what parts of the loop I might count in one chunk or the other, and let's see how that is. Like I said, maybe before the loop I might count the setup. It depends on how I do the analysis. We'll see in a second. And the after the loop I might include the exit. Again, it depends on how I want to do the setup. The reason why this depends a little bit is no matter what, in a loop, there's usually one extra step. Or maybe a better way of saying that is one extra half step. And actually, it's maybe more logical to count it on the exit here, which is the loop. Every time we actually exit or execute the loop normally, we do the checks and we do the body, and we might call that a full iteration. But then when we exit at the end, we do this sort of half iteration where we do the checks, but we don't do the actual loop body. And so as a result, there can be more than one way. Where do we take that extra half iteration, those extra checks? Do we count those as happening before the loop or after the loop? That becomes a matter of just convention and what you prefer as a researcher and a programmer. And so I leave that up to you. Now, I have started, at least in these videos, I'm going to lump it into the end. That's why I've highlighted it and putting it as the exit here. Let's see how that comes together then. So let's start out before the loop. I'm going to say before the loop, I'm just going to count these two operations, the entrance into the method, the method call, and this assignment to get started with my minimum so far variable. And then when I enter the loop, I'm going to count a full execution of the loop to be these two operations, the assignment and the comparison on the first run through, or the increment and comparison on every other subsequent run through iteration, plus the body. And again, in the body, I'm going to assume worst case, so this possibly I'm going to assume happens. So in the worst case here, I'm going to end up with two operations on this first line and then two operations in the loop body for a total of 4 operations per iteration. Okay, let's see. Okay, so we did this bit. The next bit is the bit with the 4 operations. So here I've come up with the 4 operations, and I'm going to use now the summation to also capture how many times we iterate. So that's going to depend on n. So as we mentioned before, I'm just copying this index directly down. I equals 2 to n, and the 4 comes from the fact that I did 1, 2, 3, 4 operations through every execution. Okay, so that's carrying out the middle chunk, the for loop. What about the end chunk, the after the loop bit? The after the loop bit, I'm going to say we're exiting, so that's where I'm adding that half a loop, okay, or half an iteration. So I got these two checks which come from exiting the loop plus the exiting the operation, the returning the min at the end. So I'll count those as 3 extra operations. So here I've got the 2 operations to complete the loop plus 1 extra operation. That's what we counted there. So putting it all together now, we can write it as 2 operations to begin. That's the first chunk. The for loop chunk we have as the summation plus the 3 operations to end. Okay, I'll just move the 3 out front. Notice here when we write summations, because this can be a little ambiguous. Do I mean 4 plus 3 all in brackets all being summed over? That is not what I mean. For instance, if that was what I meant, I would put the brackets on there because this is ambiguous. Okay, and because this is ambiguous, we usually don't like to write the pluses after the sum. We like to put them before the sum. So here I put it 5 plus the sum, and then we know exactly what we're summing over, which is the 4. And if you do have to write something this way, then throw brackets around it and it makes it unambiguous. We could just put brackets around the 4. That looks a little bit weird, okay? But if you need to throw them on there to make it look clear, then you can do that. Otherwise, the assumption, unless you put the brackets around the 4 and the 3, is that we're only summing on the 4, okay? But again, there's a little ambiguity in that notation, which is why we bring the 5 out front. So I've taken the 3, added it to the 2, and left it out front. So that leaves us with a choice here, or rather the last task, which is to how to solve this. Now, again, let's maybe see what rules from our summation kit that we've developed here can we bring to bear here. Well, does the 4 depend on I? And that one, hopefully we take a look and well, of course not. 4 is a constant. Every iteration we do 4 steps. So it doesn't matter which iteration we're in, it's always 4. So that means actually we can factor that 4 out if we wanted, leaving us with just the 1 in there. Okay, so that would be my next step, factoring that 4 out, leaving us with just the 1. Now this we already solved. We know this is n minus 1, right? So we'll apply that rule. If not, we can do the 2 steps we did on the previous slide, or we could plug in our formula a minus b, so n minus 2, plus 1 more gives us n minus 1. So that gets us here. So that's this trick we use often to just eliminate the sum. Now we don't have the sum anymore. And that means the rest of what we need to do is just algebra. So that's quite straightforward. We get our 4n minus 4, distributing, right, using our distributive law. And then let's just do 5 minus 4 is plus 1, and we conclude with 4n plus 1. Okay, so let's do a quick comparison. When we did our sort of more rough analysis, our high-level analysis, we said we did n plus 1 assignment operations. If we only counted the assignments, there were n plus 1. Now we said, well, what happens if we account all the operations? Well, in that case, we ended up with 4n plus 1. 4n plus 1. So now we end up with roughly, let's just wave our hand at it, 4 times as many operations. Well, what does that really teach us? I don't know what. Maybe all that means is in this minimum algorithm we've designed, that about a quarter of the operations happen to be assignments. What can you do with that information? I don't really know. I guess it's interesting to know, but it doesn't really inform us about too much. However, this expression here, this 4n plus 1, we can now use this to calculate how long we might expect the minimum algorithm to take on different size lists. Say we have a list of size 100, for instance, we might say, well, this is going to take about 401 steps then for us to find the minimum. And maybe that might be useful. And again, we're going to take this formula, this function here, 4n plus 1, and we're going to do a little bit more to it later because sometimes these details, the details about the 1 and the 4, are still details that maybe are too fine detailed that we might want to toss them away later. But before we do that, let's apply that same sort of technique here to see if we can come up with summations for some of our other, well, the other two algorithms that we looked at, the sequential search algorithm and the string equals algorithm. So I thought let's do this one sort of on the side here. Let's maybe put it together one piece at a time. Now, we talked earlier about runtime functions. So in this case, I'm going to give it a name. I might call it f of n. I didn't do that in my previous example, but maybe I'll give it a name, f of n. And again, I might go look at my code here and try and count out the different operations that we're going to carry out. So let's again break it into chunks. So before the loop, it looks like we still have two operations. We have the method call and the assignment, and then we're going to go into the loop. So let's get ready for the loop. Now the loop, let's do what we did before. I'm going to copy down I equals 1 to n, right? Okay. And now I need to decide what I'm putting in here. So that means counting the operations we do in the loop. So we've got two operations as the loop overhead, if you will, the increment and check, or the assignment and check. And then, again, we have two possible operations being carried out in the loop body. So it looks like we actually have the same math showing up, at least for the most part. The loop body is going to take 4 operations. What about after the loop body? We have to exit and we have to return. Looks like we have the same again as a 3. So putting it together would give us a 5 plus this sum. And if we're sloppy and we blurred our eyes, this might look like the exact same thing as before, but it's not. We started at 2 before, not at 1. So this actually is going to give us not n minus 1 here, but n, right? So we actually get 5 plus 4n. Now 5 plus 4n, well, we usually write that as in a normal polynomial style by writing them in order, decreasing order of their degree of the terms. And so we might put the 4n first, highlighting that that's the dominant term, the most important term in the polynomial. Okay, well, what about, well, let's just see. I think we probably got the same thing up here on the slides. Okay, that's good to see. Well, what about our string equals? Can we do it again for string equals? Let's give it maybe a different name. I'll call it g of n. Okay, and in g of n, again, let's go through. Our 3 algorithms we've designed are actually fairly similar. So hopefully we're not getting too surprised here when we see that the analysis is coming out to be fairly similar as well. But actually here it looks like we've got a couple of extra steps here. So let's be careful. We've got the method call and an assignment. Those were the 2 we had before. But now we actually have this business. What's going on here? If n is not equal to n, then it's false. That looks like two operations here. Now here, the 2 operations, again, we're going to assume they both are carried out for the worst case. So that means it looks like we ended up with 4 beforehand. Now what about our loop? The loop itself, let's be careful, is going to be I equals 1 to n, again, copying the indexes down. And how many operations again? We have 2 on the overhead and 2 in the body. So it looks like we're at 4 again. Plus, what about exiting the loop is 3 again. So we actually get a slightly different number here. It looks like 7 plus our sum. I equals 1 to n of 4. Now that really is the exact same sum as we had up above. So we know that that's going to be equal to 7 plus 4n. We could factor it out, or we could just apply the same math that we did up above there. Okay, and that 4n, again, we'll maybe just put out front, 4n plus 7. So we've actually ended up here with 3 different functions expressing the runtime of our 3 different methods or algorithms that we came up with for these 3 different problems. The three different algorithms that, or the three different functions that we came up with, while different, are still actually fairly similar. So the 4n plus 7, the 4n plus 5, and the 4n plus 1. So what I've actually done is I've taken those functions and I've plotted a few values of them in our chart here. Now, we actually started with this in the previous video, looking at how many we might get for different values, like I equals 0, 1, and 2, or sorry, n equals 0, 1, and 2. But here, or specifically, I think we focused on 1 and 2 in the previous video for the 4n plus 1 case, and we indeed found that it took 5 or 9 operations in the worst case. And here I've just plotted what those numbers would look like as we increase n. So really, we're just adding 4 to each one as we go up until I start jumping up a bit, seeing what we would be at for n equals 10, n equals 100, and n equals 1000. And what we'll notice, why I'm bringing this up, is down at the bottom, where our difference might actually seem quite significant, the difference between 5 operations and 9 operations, or 5 operations and 11 operations, seems like quite a bit, maybe almost double. When we get up to a large value of n, where n is high, those differences are almost negligible, almost non-existent. They're less than 1%, for instance. We're up here, they might be over 100%. And so as a result, what we find is that these pluses here, the plus 1, the plus 5, the plus 7, almost seem irrelevant to what we're trying to do with our analysis, which is maybe if we sort of blurred our eyes a little bit and we couldn't see this last digit, maybe instead of 1,000 we're at 1,000,000 or 1,000,000,000 or 1,000,000,000. This last digit really seems unimportant altogether. We might even start rounding it off inside our machine. And so all of these are starting to seem like they take the same amount of time, even though their functions are different. And so we want some kind of tool to capture that all these functions are kind of the same. And in fact, we have a name for these functions already. We call them linear functions because they grow linearly. You may have heard this term before, linear functions, or a quadratic function, or a cubic function. These are different polynomials with different degrees. And while the focus in maybe calculus or a different branch of mathematics might be on a different properties of these polynomials, the focus of computer science is on the growth, how fast these polynomials grow as we increase the value n, or as n approaches infinity. And so we're going to use a tool in the next video coming up where we're going to introduce what's called asymptotic notation. Asymptotic notation says, well, okay, these are all functions, but how do these functions behave asymptotically, meaning as they approach the asymptote of infinity, as n gets really big as we approach infinity. So we call this asymptotic notation, also known as big O notation, which is sort of the more commonly known name. And so in the next video, we'll bring that up to allow us to take these functions we've created using summations to analyzing looping structures to then say, well, can we lump them together into these runtime categories like linear functions or quadratic functions? So more on that in the next video. Thanks a lot for watching this video, and we'll see you in the next video.